RBD-mirror is a Ceph feature that we've had for 3 years since the dual release as a means of asynchronously replicating RADOS block device content to a remote Ceph cluster. That's all fair and good, I hear you cry, but how do I use the damn thing? How exactly does the RBD-mirror daemon work? What's the difference between one-way and two-way mirroring? What authentication considerations apply? How do I deploy RBD-mirror, either manually or in an automated fashion? How is mirroring related to RBD journaling? How does that affect RBD performance? And how do I integrate my mirrored devices into a cloud platform like OpenStack so I can achieve true site-to-site redundancy and disaster recovery capability for persistent volumes? Well, it's great you ask, because that's what this talk is about. And I'm about to give you a rundown of the ins and outs of RBD mirroring. I'll suggest some best practices to deploy it. I'll outline performance considerations, and I'll try to highlight some of the traps and pitfalls that you might encounter along the way. My name's Florian. I've worked with Ceph since about 2012, and my Twitter handle is on this slide, and it's also on the bottom right corner of every other slide in this talk. So if you have any questions about this, then please feel free to tweet them, including my handle. And if time permits, then I'll be happy to get to your question during the talk. And if not, then I'll reply to your question on Twitter afterward. So what is RBD mirroring good for? RBD mirroring serves the purpose of asynchronously replicating RADOS block device data from one Ceph cluster to another. And now, to understand how and why that's useful, we'll have to back up a little bit and look at how replication in a Ceph cluster normally works. So as an application writes data to a Ceph cluster, it always talks to a single OSD, which we call the primary OSD, for every bit of data that it writes. And that primary OSD then takes care of replicating that write to the non-primary OSDs. So consider the flying balls here representing I/O in flight. So as long as it's not completed, meaning as long as it hasn't turned green and has been reported as such from all the OSDs, the application itself considers it not completed at all, and it remains blue. And only when we receive an acknowledgement from all of our OSDs, we consider the write operation complete, and the application turns green itself. So that is what we refer to as synchronous replication. Synchronous replication is inherently latency critical, because if just one OSD is slow, or merely slow to get to, then that can potentially hold up the entire application, basically contributes to latency for the entire application. Which is why, with very few and very clearly delineated exceptions, you really shouldn't do something like this. So this approach is known as a stretched cluster, and it means that you're operating a single Ceph cluster that is stretched across several physical locations or sites. Now, this is something that you should really only try if you have full control over your site-to-site links, and you can ensure that your latency stays within very reasonable limits, which normally is only true for Ceph clusters where all of the nodes are within the same city, and also where you have dedicated fiber connections between them. However, building these stretched clusters becomes impossible once you're having to deal with C. That is not C, the programming language, but C, the speed of light. These scientists and academics in the audience will forgive me this little cheap joke, because obviously, in fact, we're not talking about the speed of light in a vacuum, but in fiber optic cables, where it is more on the order of 204,190.5 kilometers per second. But you need to consider that the typical Ethernet round trip time that we have in a local Ceph cluster is on the order of about 100 microseconds or 0.1 milliseconds. Now, those 0.1 milliseconds, 0.1 light milliseconds in fiber, that is to say, the distance that light travels in a glass fiber at that time is just 20 kilometers, or a round trip of a link that's 10 kilometers one way. And that, of course, is assuming a theoretically perfect environment where there's no additional latency introduced by anything other than that of light traveling in a straight line fiber optic link, which you never have, between the two locations. But generally, you can't ever assume any LAN-like latency outside a 10-kilometer radius. And that also means that if your cluster sites are just 100 kilometers apart, which doesn't quite cover the distance from here to the French border, your round trip time increases tenfold versus a local Ethernet LAN. And for 1,000 kilometers, that's roughly the distance from here to Munich or from here to Lisbon, it's 100-fold. So clearly, building stretched clusters is not an option if you want to replicate your Ceph data on a continental, let alone on an intercontinental scale. So that's why, for long-distance replication, we have to take a completely different approach. And that is, we're not doing the replication at the low RADOS level, from OSD to OSD, but instead we're doing it one level up at one of the abstraction layers on top of RADOS. And in this case, I'm talking about the abstraction layer that's most important for virtualization use cases, namely RBD. And importantly, we need to be talking about replication that is asynchronous, so we don't have to worry about network latency anymore. So what we'd like to get is an RBD image whose changes are asynchronously applied in a remote location. And to get that capability, we need to track and record those changes in the first place. And to do that, we use an RBD feature called journaling. Now, RBD journaling has absolutely nothing to do with OSD journaling, which is an implementation detail of the OSD file store implementation. This purely has to deal with RADOS block device, has nothing to do with OSD implementation specifics. So the purpose of this the purpose of the RBD journal is to record all writes, that includes data and metadata changes, to an RBD image, to a journal of RADOS objects, preserving a consistent point-in-time stream that can be mirrored to other sites. So here's roughly how this works. Once you enable journaling on an image, all writes from librd go both to the original image and to a completely separate set of RADOS objects that record all modification to that image chronologically. And that journal can then be consumed by a daemon, which again chronologically applies the journal changes to a different RBD image, but we get to that in a moment. And it's important to understand that as of today, RBD journaling is a librd-only feature because client-side journaling support has yet to land in the rbd.ko kernel driver. And we're expecting that to happen within the next, shall we say, 2 to 3 kernel releases. So as of today, it's librd only. Journaling is not enabled by default on RBD images, it's in general, either you or something acting on your behalf must enable it, some automation, whatever. And the RBD utility allows you to do that with RBD feature enable. In principle, you could also make this a default. Of course, there's the RBD image features flag where you could include the bit for the journaling feature. But that's really not recommended for reasons I will get to. So generally, RBD feature enable followed by an image spec, so pool/image journaling enables this. And you can also do this on image creation or image import with the image feature flag. And you'll need to specify the journaling feature itself and also the exclusive lock feature that it depends on. It should be noted at this stage here that image features or setting image feature overrides the default feature set. So with the commands shown here, what you'll get for the images is just journaling and exclusive lock. Whereas what you probably really want is image feature, layering, exclusive lock, object map, fastdiff, deep flatten, and journaling. But I've omitted that on the slide here just for brevity. Okay? So that's what this looks like. What happens when you enable journaling, you can create or import an image with journaling enabled. In this case, we import. And then if we list the RADOS objects that belong to that image, which we'll see in a second, we'll see header and data and object map objects as usual. But we'll also see these journal objects that are created in our Ceph cluster for journaling purposes. And of course, disabling journaling, just as easy. We can use RBD feature disable to turn journaling off. And then if we do RBD info again, we verify that it's in fact off. And if we list our RADOS objects again, which is going to happen in a second, then you'll notice that the journal objects will now be gone. So we still have the data objects, the object map objects, and that, but the journal objects are gone. OK. So RBDmirror now is a daemon that watches journal updates in journal-enabled RBDs and replays the journal in the cluster that it runs in. So it looks roughly like this. We've got 2 Ceph clusters, which here I've named left and right. In both Ceph clusters, I have an RBD image. And when properly configured, an RBD-mirror daemon on the right cluster in this example is responsible for subscribing to the journal updates that are generated for the RBD image in the left cluster. Okay? And this part of the process is called watching the journal. And then it takes these journal updates and applies them chronologically to a volume that has the same name and is in the same pool, albeit in the right cluster. And that part of the process is called replaying the journal. So we have watching and replaying the journal. And in this configuration here, the RBD image on the left cluster is known as the primary image, whereas the one on the right is the non-primary image. And I should note that we can also have multiple non-primary images. So that means that we can have multiple RBD mirror daemons in multiple clusters watching the same image journal and then replaying it locally. And therefore, we can, for example, replicate from one primary to 2 or 3 non-primary sites. But in doing so, every one of those sites needs its own RBD mirror. Now, as shown here, what we cannot do is one thing, which is reverse the direction of replication. So replicate into the left cluster as opposed to out of the left cluster, because the left site in this graphic here doesn't have an RBD mirror daemon of its own. And so therefore, this is the mode that we call one-way mirroring. And to be able to reverse the replication, we need two-way mirroring, in which case we have RBD mirror daemons in both clusters. So we go from this, which we've seen before, that's one way, with only an RBD mirror daemon in the right side, to two-way, where we have RBD mirror daemons in both sides. And so therefore, any image can replicate either from left to right, in which case it's primary on left, non-primary on right, or we can replicate from right to left, in which case it's non-primary on left and primary on right. And then we can reverse that. So we can flip an image's direction of replication. So we can flip the primary versus non-primary state. And these processes we refer to as demotion and promotion. So promotion means we're making a non-primary image primary, meaning it was previously a replication target, is now a replication source. Or we can have demotion, where we have a primary image that we make non-primary, meaning it was previously replication source and is now a replication target. Now, we now know that we need a running RBD mirror that can watch journals on one cluster, replay them on the other. And that means that that daemon needs Cephix identities with very specific capabilities on both clusters. And the first thing that we'll need to do in order to get RBD mirroring enabled is create those on pre-Nautilus clusters, that is. On Luminous and Mimic, we have to do this either manually or some deployment automation has to do it on our behalf. In Nautilus, this just got a whole lot easier because now the RBD mirror daemons are stateless and they keep all of that information is kept internally. But as we saw from a poll this morning, apparently not all of you are running Nautilus yet. So that's why I'm talking about pre-Nautilus releases in this talk at length. So this needs to happen on both of, or rather all of the clusters that are involved in replication. We create here a client RBD mirror, some unique ID user or Cephix identity. And we give it the MON profile RBD mirror and OSD profile RBD capabilities. And that ensures that that instance can participate in mirror peer discovery and mutual authentication. That's what the MON capability is for, among other things. And they can read from and write to RBD images in all pools. That's what the OSD capability is for. And now this is relatively easy because we have capability profiles now. In earlier releases, this would have been more difficult because we'd have to set them up with individual capabilities. Now we have the cap profiles. Great. So that's relatively easy, relatively simple. What is a little bit trickier is enabling the RBD mirror instances to find these authentication credentials, which largely means getting the keyring locations right. So first, this gets a bit complicated. So first, on whatever nodes you are going to be running RBDmirror, the daemon is going to have to be able to access the local cluster, and therefore it will need to find its keyring in the default location. Now, I'm sure many of you will know that the default keyring location path name is constructed like /etc/Ceph, cluster name, type, ID, and then .keyring for the full file name. And my RBD-mirror daemon is actually a client to both the clusters that it talks to, hence its type is client. So if you want to call your RBD-mirror daemon RBD-mirror foo something, then the proper keyring location for the daemon to access the local cluster would be etc Ceph, Ceph for the local cluster name, client for the type, RBD-mirror foo for the ID, and then .keyring. So far, so simple. But the RBD-mirror daemon also needs to access the remote cluster, and this is the part where it gets a little bit complicated, because first you're going to have to tell the RBD-mirror where to find the remote cluster. That's relatively simple, because all it needs to find is the mon hosts. And so you can give your RBD-mirror node a relatively bare-bones Ceph client configuration by dropping a configuration file that is now not named ceph.conf, but remoteclustername.conf into etc Ceph. So for example, if you want to connect to the right cluster from the left, you might call this etc Ceph right.conf, and you put in the mon hosts for that. And then it needs to find the correct keyring for connecting to that cluster. And this follows the same naming convention as before, but now we don't use the default cluster name of Ceph, but a different one. So for example, it might be etc Ceph right client RBD-mirror foo keyring. And then we have to do that in reverse on the other side of the replication link as well. So that sounds complicated, and it is, but it's really quite logical. But good news is that most of this you actually don't have to do in Nautilus anymore. But if you want to do this with Luminous and Mimic, that's what you need to do. If you're setting up RBD-mirror manually, or you're troubleshooting what your deployment automation set up for you, or you're troubleshooting RBD-mirror authentication issues in general, then this is what you can do to do that. You should always be able to contact the local cluster and the remote cluster. So if you do ceph-id rbd-mirror.uniqueid-s or --status, then you're connecting to your local cluster as RBD-mirror, and that should return a result. And then if you do ceph-cluster right ID something or other -s, you should be able to see the remote cluster status. And the same should be true in reverse. Now, with all those prerequisites squared away, we can discuss what needs to happen in order to actually start replicating. And this depends somewhat on your deployment automation facility. It might be automated away to various degrees. But it still absolutely doesn't hurt to know what's happening under the cover. So the first thing that we need is we need a way to reliably start the RBD-mirror binary. And if you're running on a conventional, that is to say a non-container-driven deployment scheme, the RBD-mirror binary is normally started from systemd. And as such, the package deploys a systemd unit file. And this is how you enable or start an RBD-mirror service that's managed by systemd. Relatively straightforward. And something that you probably never want to do manually is run RBD-mirror in the foreground. If you have to, this is how you do it. However, this is also how application containers invoke RBD-mirror. So if you're using the Docker container approach that Ceph Ansible uses, if you so choose, if you tell it to, or you are using Rook, this is how it would invoke, by and large, this is how it invokes RBD-mirror as a foreground daemon. And then you need to enable it. So even if you have RBD-mirrors running, RBD-mirror daemons running on all your sites, mirroring is still not enabled by default on your cluster. And you switch it on and off on a per pool basis. So you switch it on and off for each pool that you want mirrored. Again, this is something where you have two options, which is you can choose pool mode mirroring. And in pool mode mirroring, all images in a pool are automatically mirrored, just so long as they have journaling enabled. And you can also do image mode mirroring, and that means that you're basically tagging the pool to be mirrored, but you still have to enable it individually on individual images. So for this to work, RBD-mirror pool enable pool and then the mode keyword image, what has to happen for every image that you want mirrored is it has to have journaling enabled, and it also has to have mirroring explicitly enabled. There's an RBD-mirror image enable command for that. And then you'll need to connect RBD-mirror instances to one another. And we refer collectively to RBD-mirror instances that are meant to talk to each other as peers. But I would strongly caution against using the term peering for this process. because all you're going to cause is a royal amount of confusion if you're talking to someone who is not yet familiar with RBD-mirror, but who is familiar with the concept of PG peering, placement group peering, which is a completely different thing. Okay, so just don't call it peering, say connecting peers instead. And for connecting peers, you've got basically two options. You can do everything from one host, or you can first shell into one and then the other, whichever you prefer. So you do RBD-mirror pool peer add, and then for a pool, you add the peer. And then if you want two-way mirroring, you also do that in reverse. So you can either connect to the other cluster from your Ceph client, or you can just shell into one and then shell into the other. And then here's that screencast loops. So that's an image with mirroring enabled, right? You do RBD info, and once you do have both journaling and mirroring enabled, then you see not only the features, not only the journal ID, but also the mirroring state and whether we're mirroring or not, and whether we're mirroring primary or not. And also, you have RBD-mirror status. That gives you a little more information about the status of replication, such as the current state that the journal is at as it's replaying. And then I mentioned before, we can demote and promote images. So once the clusters are properly connected, replication is active, then you can influence the direction of your replication. So if you have an image that's currently primary and you want to demote it to the non-primary status, you do that with RBD-mirror image demote. Or you can also do that for all images in a pool with RBD-mirror pool demote. And the reverse is called promotion. And that's RBD-mirror image promote, pool/image, or promote all of the images in the pool with RBD-mirror pool promote. Now, an image must be demoted on one side before it can be promoted on the other, obviously, except in the case that its peer is down or unreachable. So something actually knocked out your primary cluster. You now need to promote all of your mirrored images on the other site. In that case, you can force promotion with the --force option. However, in case the peer site subsequently recovers, there is no automated mechanism to reconcile the image content. So you basically have to decide which images you want to resync, and then there's an RBD-mirror image resync for that. Now, with all of what I said in order about what you need to do in order to deploy RBD-mirror manually, which of course in reality you really don't want to do, here's a very quick look at what individual deployment automation facilities for Ceph do about RBD-mirror. And I'll start with Ceph Ansible. Ceph Ansible lets you create and deploy RBD-mirror credentials and capabilities and keyrings and all that. It also deploys the RBD-mirror daemon for you, and it can also automatically connect your cluster to a remote one. It does also help you with keyring exchange and remote cluster client configuration. So it does give you the tools to fully automate a cluster pair, but only if you thought to set two different cluster names from the get-go. And if one of your clusters is already deployed and uses the name Ceph, there's some manual intervention that's required before you can then manage everything else with regards to RBD mirroring with Ceph Ansible. And of course, promotion, demotion of individual images are completely outside Ceph Ansible's scope. There's something that very recently happened in Juju land. So in Juju, there is now a Ceph RBD-mirror charm. It's brand spanking new. That can automate the entire RBD-mirror lifecycle. That includes the daemon deployment, key exchange, with Juju offer Juju consume, failover and failback. So promotion, demotion with Juju run action, and so forth. It's basically meant to be sort of a full lifecycle management tool for Ceph RBD-mirror, and looks pretty neat. DeepC currently supports no RBD-mirror automation facilities whatever. However, if you happen to be on SUSE Enterprise Storage, which is deployed with DeepC, then your supported RBD mirroring deployment automation facility in SUSE Enterprise Storage 6 and later is just the post-Nautilus or Nautilus Plus Ceph dashboard, where you can do all of that from the dashboard. And with Nautilus, you also don't have to worry about, with the stateless RBD mirror daemons, there's a lot less to worry about with key exchange and blah, blah, blah. So basically, from SES6 forward, as I understand it, you don't really need DeepC to manage RBDmirror because Ceph by itself and the dashboard can essentially do it quite nicely themselves. And finally, Rook is also capable of managing RBDmirror instances and configuring them, but it does currently rely on a cluster administrator running the RBDmirror commands for peer-to-peer connection and pool and image actions. So now, about the performance implications of RBD mirroring. I have good news and I have bad news. So the good news is RBD mirroring really doesn't have a major impact on an image's performance, right? It's barely measurable. The bad news is journaling, unfortunately, absolutely does. And you can't have mirrored volumes without journaling, right? So you have to take this into consideration. So what I'm talking about, sorry? OK. So what I'm talking about next, the data that I've compiled for the following slides are from RBD bench runs. They were all run against a single 1 gig RBD image using the default order of 22, so a 4 megabyte object size, which ran on an all SSD all Blue Store Luminous cluster, which used the same pool for the journal objects as the data objects. You also have the option of splitting those, basically write your journal objects into a different pool. I didn't do that here. And these benchmarks were run with the default setting of 16 I/O threads. They were run in sequential and random read and write mode with the I/O size, with the I/O sizes varying up. No, sorry. There we go. With the I/O sizes varying from 4K to 4 meg. And it's important to understand that none of the absolute numbers in these results should be considered dependable benchmarks, and you shouldn't compare them to your own cluster. And they might differ wildly based on what hardware you use, what configuration you use, etc. My point is simply to show the impact that journaling has in relative terms versus running non-journaled RBD. So again, good news first. With reads, well, I should perhaps explain here what you see on these charts. All of these charts, we have the I/O size on the x-axis. That goes on a scale of powers of 2, from 4K to 4 meg. And the y-axis, which is linear, that has either bytes per second if we're dealing with throughput, or IOPS if it's IOPS that we're looking at. The black line is always what we get without journaling. The red line is with journaling enabled. Okay? And so I promised good news first. So here's some good news. There's very little impact that RBD journaling has on image reads, right? So if you have a read-heavy workload, then that shouldn't expect to suffer very badly when RBD journaling is enabled. And that is true for sequential reads, what we see here, the throughput of random reads, and also read latency, and hence IOPS, are not extremely heavily impacted by journaling, whether we're dealing with sequential or with random reads, right? But for writes, we're in for a bit of a rude awakening. Okay? Now, generally, if we're writing our data and our journal objects to the same pool, which we are in this case, then we're sort of assuming our throughput to be roughly halved because we're writing everything twice. That's what you see on the right-hand side of the chart. So it's true for rather largish I/O sizes, from 128K to 4 meg is around about that territory. But for small writes, the overhead is really quite astounding, right? You might be dealing with an overhead of a factor of 10 for 4K writes. Now, there is something you can do to address this. You can, and this is word from this very conference, so, which is there are some librd client-side options that you can set that determine under what circumstances the RBD journal is being flushed. And all these RBD journal object flush parameters default to 0, which means essentially flush the journal after every write. And of course, when we're dealing with a great deal or a great number of small writes, that has a pretty significant impact. And in pre-Nautilus, this would be something that you'd need to set on every single client, whereas from Nautilus onward, you can set it centrally with cluster side configuration, because that also propagates to the clients. That, however, is something I've yet to test. Okay, same pattern expectedly manifests itself for random write throughput. Sequential write IOPS, we're also seeing that 9/10 reduction for small writes. That's on the left of the chart. And again, for random writes, it looks just a little less than what you'd intuitively expect, but it's still quite significant for small writes. Just so you believe me that it's really journaling that makes the difference and not mirroring. What follows are some benchmarks with mirroring enabled. Those were taken on different machines. There were virtual machines even with file store. The absolute numbers are basically completely junk. But the relative comparison versus non-journaled and journaled but unmirrored devices should still be useful. I'll go through these really quickly because you'll catch the gist really fast. Just look at how close the blue and the red line are. Right, so black is still without journaling, blue is with mirroring, and red is still with journaling but with no mirroring, right? And so, like I said, mirroring and journaling doesn't really make much of a difference. So reads, nothing at all, but then for writes, here again is the rude awakening. And again, black is no journaling, red is with journaling, and blue is with journaling and mirroring. As you can see, between those two, not a gigantic difference. And here as well. Okay, so I will humbly suggest this takeaway. If you have really good reasons for enabling journaling on your devices, such as selectively mirroring individual volumes, and you have weighed those expected benefits against the performance implications that I just talked about, then do that. But don't, under any circumstances, enable it globally or just on a whim, because chances are that your customers are going to hate you for it. Okay? Again, I need to reiterate Luminous and my hardware and what have you, but my slides include the backup slides here if you look them up. They include the benchmark scripts. So if you want to replicate this, then you're certainly welcome to do so. And then finally, I have some thoughts on the integration of RBDmirror with cloud applications. And I only have a few minutes left, and I consider myself qualified to only talk about OpenStack rather than any other cloud platform. So that's what I'm going to be talking about. So first up, in OpenStack, the definition is that any persistent data needs to go into a volume. And therefore, everything that is not in a volume is by definition ephemeral. And so that means the only user-generated data that's persistent is in Cinder, right? And in Cinder, which is the block storage service in OpenStack. And in Cinder, we have the concept of replication, which you have to define by adding this replication device stanza to your Cinder backend configuration. And that's totally supported for the RBD driver. So you can totally have a Cinder interface with RBD mirroring and RBD mirror managed volumes, which is admittedly a bit under-documented, but generally works. In such a way that your OpenStack environment can use a primary and a standby Ceph cluster to talk to. And it can even fail over volumes between one and the other. Does this get me full automated disaster recovery capability, as some claim it does? To wit, an OpenStack environment where you can lose an entire site and you can then, within a reasonable time frame, bring up all of the VMs and resources in another site without any intervention from end users. Whenever I read something like that, I maintain it's a bit of hand-waving, and I personally have yet to see it work anywhere, but I'll be more than happy to stand corrected, because frequently at least one of those Ceph clusters is going to be co-located with an OpenStack cluster, as in this example. And then here, if a major issue happens to the left site and it takes out both OpenStack and the locally attached Ceph cluster in that site, so say plane crash, flooding, whatever, then you have your data in another site, but you have no way to restore service, right? Because you're simply lacking the compute nodes and the networking hardware and whatnot over in the other site. And even if you do have OpenStack in one site and the other site and a Ceph cluster in both and you're replicating data between them, then you can still have no automated failover unless you also replicate your OpenStack metadata. So just having a mirrored volume named volume some UUID in a pool isn't going to help you a whole lot if you're lacking all the metadata that's related to that volume, such as what OpenStack tenant does it belong to, what VMs is it attached to, and so on. So do I really have no way of doing this? Well, I think we do. But to be fair, what follows is also hand-waving, because I've not implemented this in production. But it's the only way that I can imagine for this to work. But you'd have to do it from the start, from where you first stand up your OpenStack environment. And you have to get it right immediately, because there's practically no way to add this as an afterthought, right? So this is, I maintain, your checklist for actually building DR capability into your OpenStack environment using RBD mirroring. You're going to need one logical database that spans all locations that holds all your metadata. So either you have 2 OpenStack and Ceph sites and a third one that runs just Galera, or you've got 3 sites anyway in the first place, and you replicate between those with Galera. You're going to need OpenStack API services in all those locations. And you're also going to need availability zones by site for all those 3 locations for Nova, Cinder, and Neutron. You're going to need compute nodes and network gateway nodes, plus independent provider uplinks in all those locations, plus a dynamic routing protocol like BGP, so you can arbitrarily announce routable IP addresses either here, there, or there. You're going to need management, tenant, and storage network layer 3 connectivity between all locations. Nova, Glance, and Cinder in all those locations must be wired up to their local Ceph cluster. And then you have to set up 2-way pool-level replication for your Nova, Glance, and Cinder pools. And you have to auto-enable journaling on all RBD images created in those pools with the performance implications that I previously discussed. And then you have to have automated scripting in place so that when one site goes down, everything linked to that availability zone is reassigned to a different one and then spun back up there. So not undoable, but probably more expensive than you think. OK? I'll tackle my Twitter very promptly for your questions. But before I do that, as pretty much all my presentations, this deck is Creative Commons licensed, Creative Commons attribution share alike. This is where you find them again. And finally, I'd like to add a few acknowledgments for some people who kindly provided feedback and input on portions of this talk. So how are we doing on the question list? There we go. OK, there's only comments on Twitter. Great, but those are not questions. So thank you very much for your time. Enjoy your coffee. And if you do have any other questions, then please find me after. And have a great rest of CephLoCon. Thank you.